So from last time we saw this very easy semigroup, the n squared doesn't have the reduced one doesn't isomorphic to the most natural universal one you can define. So the idea is, well, we need to put some more restriction, and this is just the motivates the study by Andonika back in the early 1990, where he realized that if you look at the left regular representation, okay, so your these kind of semigroup, they have some nice structure in terms of their left regular representation. And there's some kind of lattice structure. Well, not exactly a lattice, so that's why he called it quasi-lattice order. Okay, so those kind of structure are important. Those structure are being encoded by the left regular representation. But unless you have something when you try to define the universal one, it will get lost. Okay, so you want to encode these lattice structure as well. So that's his original motivation. So let me just briefly talk about what is a quasi-lattice order. So let's recall that we have a semigroup. So let's always assume it's embedded inside G, and we always assume that P, well, the only thing that's invertible is just the identity. And so this P, you can think about P as one way is that it defines a partial order. So partial order on the G. So think about the natural number. It determines the order of the integers. What do I mean by order is that one thing is less than the other if their difference is positive. Okay, the bigger one minus the smaller one is inside the set of natural number. That basically defines your partial order. And in general, you can do the same. So you can define a partial order by saying x less than or equal to y. So x, y are both inside G. If your x inverse y is inside P, okay? So this partial order is left invariant, okay? So because what I mean by left invariant is that if you multiply P on the left, okay, then you can still have this inequality, okay? So if x less than or equal to y, you can multiply P on the left, okay? That doesn't change anything. And equivalently, there are many ways of think about this. One way is that your x inverse y is essentially inside P. That's just equivalent to saying your x inverse y is equal to some P inside your semigroup. In other words, your y, you move the x to the other side, your y will start with the x part. Okay, so x is some kind of called the initial segment of your y. Okay, so your y can be started by this x. And another thing is that if you could just consider all the things that's obtained by multiplying your semigroup element to y, okay, so this is sometimes called a YP, sometimes called the principal ideal or principal right ideal. Okay, so this one is going to be, well, it's going to be smaller. Okay, so it's also contained in the XP. Okay, so these two are all equivalent to each other. These principal ideal ideas really natural later on. Okay, really just motivated by Nika's work. But back then Nika didn't really mention them. Okay, but we're going to see where they rise up when we talk about the left regular representation in the next video. But in any case, so let me first give you the definition of a quasi-lattice order. Let's consider this pair. Your G is the group where your semigroup is embedded in. It's called a quasi-lattice ordered group. Okay, let's call it QLO, quasi-lattice ordered. If the following thing happens, so if for every f inside the G, say finite, so because you have a partial order, you can talk about its upper bound. So if f has an upper bound, let's say inside the P, inside your semigroup, then it has a least upper bound. Okay, so f has a least upper bound. This is denoted by using this lattice notation, V of f. Okay. All right, so this is essentially putting some kind of lattice structure. It's only half of the lattice. So if you're from algebra, you know the lattice have a meet and they have the joint. Okay, so this is quasi-lattice order is only half of it. Okay, and Of course, lattice usually require any two element has an upper bound, and the quasi-lattice order doesn't require that. Your elements may not even have an upper bound inside P. That's allowed as well. So that's the choice of the quasi-lattice order. Okay. But in any case, there's Nika original definition is this. Okay, so he insists the P to be embedded inside the group. Recent year, we have been really move on away from this embedding. Okay, so sometimes there's another notion called a weak quasi-lattice ordered. You don't need to think about all the finite subset of the group. Okay, because sometimes the semigroup satisfies this quasi-lattice condition, but not the group. Okay, we don't know whether the group satisfies that, and usually moving to the group is kind of difficult. So that's why there's recent year there's a notion called weak quasi-lattice order. So it says if every F subset of your semigroup has an upper bound. So let's just say upper bound. That would imply there's a least upper bound. Okay, least upper bound is also denoted by this V of F. Okay. All right. Any case, the weak quasi-lattice order is slightly easier to work with. It's essentially saying the following. So that's the equivalent to for every x and y inside your semigroup. If your xp, if you consider their principal ideals, then there are two things. So if they have no upper bound, meaning there's nothing that start with x and nothing start with x and y at the same time. So it just means their intersection is equal to empty. So this is case corresponds to x and y have no upper bound. Okay, it just means their principal right ideal, their joint is intersection is empty. If they have an upper bound, so it means if it's non-empty, then it has to be at least one. And by the least one, you can convince yourself this is really has to be another right principal ideal. So if the xy have an upper bound, and so basically Z is their upper bound, let's say Z is equal to xvy, then you have this intersection is another principal ideal. Okay, so this Z is the least upper bound of x and y. Okay, so that's essentially what quasi-lattice order mean. Okay, so if you think about all the example we had, the natural number, of course, satisfy that. And moreover, if you consider was the nk inside zk, that's also going to satisfy this quasi-lattice order because, well, it's really because each coordinate you have is kind of order. So if you have x1 up to xk and y1 up to yk, and you want to say, well, of course, because n is a billion, so it's quite easy to see every two thing has upper bound. And the least upper bound is really just the maximum of each coordinate. Okay, so you have xi and yi, and you take a vector like that. All right, and that way you do have an upper bound. Okay, so it's quasi-lattice order. And the nice thing about that is that a lot of other semigroups are also quasi-lattice order. So for example, the free group or the free semigroup, okay, is also quasi-lattice order. Why is that? Is that if you take any word, so free group, basically free semigroup is basically generated by k alphabet, and you think about the x and y inside these fk plus to be two kind of words consists of a bunch of alphabets. And what's their principal ideal? If you think about what happens when you multiply the semigroup on the right, is essentially just all the word that start with x, and you intersect all the another set, which is all the word that starts with y. So this is essentially all the word that start with x and y. Okay. But well, if your x is the first letter, say E1, and your y is the second letter E2, then clearly there's no word that can start with both E1 and E2. So a lot of time, this intersection is going to be empty. Of course, unless your x is initial segment of y, or y is initial segment of x. Okay, so in fact, this is going to be empty. So when it's not empty, it's just equal when x is less than equal to y, or y is less than equal to x, because things are highly non-abelian here. So when Y is the bigger one, basically longer words, then their intersections. Clearly, everything starts with Y. And when X is bigger or longer words, then you have the things start with X. Okay, so in any case, uh, only when X and Y are comparable inside your semigroup, you have their intersections non-empty, and of course, they're when they can be compared, then their least upper bound is just the bigger one of the two, and all the other case, you get something that's empty. Okay, so and just convince yourself this just fits in the definition of the quasi-lattice ordered, and that's why this is also a quasi-lattice ordered group.